Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to be looking in a little bit more detail at the equilibrium constant. So I'm going to be focusing in on some nuances of using equilibrium constants and some common vernacular you should be aware of when working with unusual systems. So one of the first things to keep in mind is when you're constructing an equilibrium constant, technically it's given as the concentrations of products over reactants, but all those concentrations are typically given as activities. So activities is essentially a special catch-all word for saying the relative concentration of a species. And one of the things that makes it very unique is that it applies differently to different phases of matter. And this is kind of what we've seen with equilibrium constants before. So for example, if I'm looking at a gas, the activity of a gas is given as the pressure of that gas over the standard state pressure, so 1 bar. If I'm looking at a aqueous solute, so in this case, something like HCl, it's typically given as the concentration in molarity over the standard state concentration, so 1 molar. And one of the big reasons why we have these standard state conditions is essentially to help cancel out units. Now, we don't quite need that for liquids and solids because they're simply given as mole fraction. So as long as I know the mole fraction or relative concentration of, say, in this case, iron in that solid, or oftentimes something like water in a liquid, then we should be fine. But as we've seen last chapter, generally when working with something like liquid water, it's close enough to assume that the mole fraction of water is going to be 1. And similarly, we can apply this to solids. So as a result, if I'm looking at the full reaction of reacting HCl with metallic iron, this ends up producing essentially a kind of iron chloride rust and flammable hydrogen gas. So typically this equilibrium expression looks kind of messy. We have concentrations, we have lots of normalization units, we have mole fractions and pressures. It's a bit messy. But as long as we keep in mind that all our concentrations should be molar, all our pressure should be bar, we can go ahead and drop out all those standard states. In addition, we can assume that most of our solids, their mole fractions are 1, so they also won't play a role in the expression. So I go from this much more complicated expression to a much more simple one, where I'm just focusing in on my aqueous species and any gases. Concentrations for the aqueous, pressures for the gases. And you'll note that the equilibrium constant has no units, despite the fact you can quickly note the units shouldn't cancel out from this expression. The reason why, all of the canceling units are there. We just drop them for convenience because that's a very messy expression to write all the time. So unless I specify otherwise, you can go ahead and just use this more condensed and useful formalism. However, one of the things you should watch out for is while the equilibrium constant, so our just standard K, encompasses both pressures, mole fractions, and molarities, you often run into special cases where all of our reactants and products are in the gas phase. Or we have a mix of gases and solids. Well, in this case, our equilibrium constant should be given in terms of pressures. However, it's very common, and especially for your book, to refer to this type of equilibrium constant as Kp. Just making sure to denote all the equilibrium concentrations are given as pressures, not concentrations. Please note, anytime you see Kp, this is the same thing as K. It's just a clarifying notation that a lot of resources like to use. And one of the reasons they use it is because sometimes chemists get lazy and it can be kind of hard to measure, say, the pressure of, in this case, dinitrogen tetroxide essentially dissociating. I may know the volume of the container and I may know the number of moles, but I might not bother to measure the pressure. So if you say know the mass of a gas in a fixed container, you're more likely to give the concentration as a molarity instead of as a pressure. So we can denote this difference using Kc. So Kc is essentially just saying any gas phase species are going to be given in molarity. And again, if you have an aqueous species, it will be continued we will continue to give that in molarity, and we're just going to ignore any sort of solids or liquids currently. So let's go ahead and take a look at the relationship in between this Kc and Kp, because it turns out these values won't be the same. And we can go ahead and show this by using the ideal gas law. So we know our K, or Kp, is going to be this ratio of pressures. Well, assuming the system is relatively low pressure, I can go ahead and use the ideal gas law to treat the system. So then I can express that pressure as the number of moles, the volume of the container, and RT. And we can do the same thing for our reactants. However, it is worth noting both our reactants and products should share the same container, so that volume won't actually be different in between reactants and products. So what we can do is give this as a ratio of the molarity of our products over the molarity of our reactants. And watch out, because we have these extra RT terms. So we have two RT terms that come from the products, because I have two products. And we have one RT term that comes from the reactants. So one of these RTs cancel out, and we're left with essentially our Kc times RT. And again, that just works for this reaction. But we can extend this into a more general formalism, that we can relate our K, or Kp, to the concentration equilibrium constant times RT times the change in the number of moles of gas. So if I end up producing gas, we'll have RT, either 1 to the first, second, third, or fourth power. However, if I end up consuming extra moles of gas, then this delta V will be negative, and we'll have to divide by a power of RT. So to illustrate the difference in between Kc and Kp, let's go ahead and look at the decomposition of dinitrogen tetroxide. So the Kp value is about 0.114. So this doesn't look too bad. I mean, it favors the reactants just a little bit. However, if we put this in terms of molarity and use Kc, then we're going to note that we highly favor the reactants much more than we previously thought. And one of the reasons why is because we have different reference concentrations. So again, a 1 mole per liter solution is going to be a lot more concentrated than a gas at a simple 1 bar. So next time, we're going to go ahead and try and apply these equilibrium constants by comparing them to our good old friend, the reaction quotient. Until then, take care.